In this video I'm going to look at using the method of componendo and dividendo to solve, or rather to integrate Monge's equations when we're trying to solve a first order quasi-linear PDE. So what is componendo and dividendo? Well, this is a simple property of fractions. So imagine that we know that we have a ratio A over B is equal to C over D. Then we can write, so if we mix together the numerators, so with some 4 factors lambda 1 and lambda 2, so here I've got lambda 1a plus lambda 2c, and then divide through by the same, by the denominators in the same proportion, so we've got lambda 1 times b plus lambda 2 times d. Then this new ratio is exactly equal to our original ones, so a over b, or of course c over d. And I should say here that these lambdas, lambda I, so these are any suitable functions. So often we'll think of them as being constants, but in the context of solving our PDEs, they could be functions of x, y, and u. Okay, so let's think about our Monge equations. And we're going to write these down in the following form. So dx divided by a is equal to dy by db is equal to du divided by c. So previously, when solving first order quasi-linear PDEs, we've sort of paired these up to form dy by dx to make a characteristic ODE. Or to make 3 of them, then we choose 2 to solve. So here we're going to do something different. We're going to use the method of componendo dividendo. So use componendo dividendo to produce equations that we can simply integrate. And that's the idea here. And so, as I often like to do, I'll show you how this works by means of an example. So let's imagine we're given the following partial differential equation. So we've got y plus u times du by dx plus y times du by dy equals x minus y. Okay, so the first thing we do is write down our Monge equations. Monge equations from this. So we've got dx divided by, so this is a, the coefficient of du by dy is b, and this on the right hand side is c. So our Monge equations are dx by a, so this is y plus u here, and this will be equal to dy by b, and b here is y, and finally we have du by dc, so this is x minus y. Okay, so let's use our technique, our new technique, and let's apply it to these first 2 terms here. So I'm just going to write C and D for componendo and dividendo. So C and D with the first two. So this would mean building the following ratio. So lambda 1 times d by dx plus lambda 2 d by dy, and then the denominators in the same proportion. So lambda 1 times y plus u plus lambda 2 of the second denominator, which is just y here. And we want an equation, so let's say this is equal to, all three of our original ratios, but we'll just take this third one. So this is du by x minus y. So it looks like we've just made our lives more complicated here by introducing this, these lambda 1s and lambda 2. And the idea is that now we choose this lambda 1 and lambda 2 to simplify things. And here you sort of need to, have a, look with what you're dealing with, use a bit of experience, a bit of trial and error. But we can see here that, so there's sort of two things to look at. If we look at this denominator here, we've got x minus y over here, and then if we compare it with what we've got on the left hand side, we've got lambda 1 times dx plus lambda 2 times dy. So if we were to choose lambda 1 equals 1 and lambda 2 equals minus 1, then we'd have dx minus dy on the left hand side, and that's of course the differential of x minus y. So that would sort of match up left and right hand sides, which is what we're trying to do here to simplify things. I could also look down the bottom. I could look at this denominator here and think, okay, well, how can I simplify this? And again, we see we've got a y here and a y here. So if I were to choose lambda equals 1 and lambda 2 equals minus 1, then these y's would disappear, and what I'd be left with is this u, and that sort of matches up with this du on the right hand side. So that's the kind of the kind of simplifications you're looking for here. So let's write, so I can simplify so if I choose lambda 1 equals minus lambda 2, so that would actually do the job, but let's set, for concreteness, let's set this equal to 1. And then if I plug that into my expression, I get dx, and lambda 2 is minus 1, so this is minus dy. In the denominator, well, we've said that this just boils down to u when I make this choice, and the right hand side stays where it is. Then I'm in a position to rearrange. So let's just bring the x minus y onto the left hand side. The derivative here, so I've got dx minus dy, so this is just d of x minus y. And then I can bring the u up to the top as well, so this is on the right hand side, u times du. And then this is something I can immediately integrate without any particular sweat. So this is, it's as if I could replace x minus y with a dummy variable v, say, then I'd have v dv here, then I can integrate that up. I'll just do it in one step. This is x minus y all squared, should have a half here, but on the other side I'm going to get u squared with a half, and then I'll just cancel through that half, and write my constant as C1. Okay, so I can just integrate that through immediately. So that gives me one of my constant surfaces for my PDE. And as you know, we need to find a second one. So the second constant surface. Let me write out my Monge equations again so you can see where things are coming from. So I've got dx by y plus u equals dy by y equals du divided by x minus y. So this time, so similar trick, but I'm going to compose and divide these two guys. And so here we can see, so we're going to be adding together some proportion of these two and the same proportion of add together the numerators and add together the denominators in the same proportion. So you can see if I just take dy plus du, that's the differential of y plus u, which I've got on the left hand side, so which I've got over here. And if I add the two denominators together, I get y plus x minus y, so the y's cancel, which just leaves me with this x, and then that x will match up with this, this x over here. So in other words, I can do my dividendo, componendo with lambda 1 equals lambda 2 equals 1. So that involves doing dy plus du, adding together the two denominators, and that's y plus x minus y, so that's just x. And then equating this to one of my original ratios. So, and here I'm taking the one that's dx by y plus u. So now the hard work's done. So once we've seen the combination, how to combine the fractions, the work is done essentially. So we can rearrange this as y plus u times d y plus u is equal to x dx. This we can integrate, so exactly the same story as before. So I've got y plus u all squared equals x squared plus c2. And again, I've gone through with a half there. Okay, so now I've got these two constant surfaces. And just to finish off the story here, so once I've got these c1 and c2, I know that my general solution I can find by writing c1 equals an arbitrary function of c2. And so for the case in hand, I've got x squared, x minus y all squared minus u squared equals arbitrary function y plus u all squared minus x squared. And as I always say, tell me if you introduce some random symbol, tell me what it is. So this is an arbitrary function. Okay, finished.